Welcome to Day 2 of MIPI DevCon 2020. We're glad to have you back. Feel free to interact with the presenters and attendees by using the engagement tools at the footer of your screen. Use Q&A to engage with the presenters and group chat to communicate with attendees. You can minimize and maximize each icon by simply clicking on each icon. To view the agenda and see the sessions and demos for today, click on the call to action icon. Enjoy the conference.
Hello everybody, my name is Stefan Moosberger. I'm an applications engineer with BitifEye Digital Test Solutions, and today I will give you a brief introduction in our MIPI C-PHY receiver test solutions and how we can actually effectively generate the waveforms and other signals that are needed to stress and test your devices. So we'll first of all go over the overall MIPI C-PHY 2.0 receiver tests, what's needed, what we have to do here, then what comes up as new challenges with those 2.0 receiver tests, and finally, yes, how actually we can resolve these challenges in an effective way and manage all those tests that we can, nicely characterize our DOTs. So first of all, C-PHY, again, the quick overview. Of course, most of you who are already dealing with C-PHY know about that, but of course, not everybody is directly dealing with C-PHY, but with all these other aspects of MIPI. So I want to give that quick overview. What is C-PHY again? What are we using here? Yeah, it's similar to DeFi. It's also for cameras and displays to transfer signals here, but for more high performance, cost optimized, higher data rates are supported here. And yes, we are using here embedded clocking. And the most challenging part, which I was actually pointing out here, is our data rates that we are now with 2.0. We are at up to 8 gigasamples per second. And for that, we have to deal with CTLE equalization on our receiver side, which of course is a challenge for actual receivers, but also for actually generating test signals. We have to calibrate it, which is also not straightforward. And we really have to hardly work on that one. So let me go a little bit deeper into those things, what we have to do here. So basically, what is a receiver test? Well, of course, we are sending signals to a receiver and then have to check what our device does. And therefore, in C-PHY, we have similar to these other MIPI standards, we have low power and high speed tests. And for both, we have to generate stress signals and then also verify the timing when switching between those kind of signals. Let me first talk about the actual stress signals. So, the stress is all about jitter, and jitter in C-PHY is modeled out of the channel itself, and then all those various jitter that is generated by the MIPI source, and both of that has actually to be taken into account when we are generating our stress signal. You see here actually that we have our channel signal that is modeled here with our ISI DCD and the generated jitter here. And basically that all depends on how the rising and falling edges are delayed or not delayed when going back and forth. And therefore, we are generating that what we are calling the effective jitter, which is the combination of all those kinds of jitter sources combined, which are close the inner eye opening, which then make it difficult for the receiver to receive the signals. To do this, we have to generate a 3-wire signal in MIPI C-PHY, which makes it a bit hard to use standard equipment like a bit error ratio tester, which just has digital signals. So we have to deal with an AWG, and we have to embed S parameters in our signals, which is also not straightforward. We have to make a calculate our arbitrary signals. So it first of all has those 3 levels on the 3 wires. And on top of that, implement the channels with S parameter simulations. And at the end, also, what is very important, we have to switch back and forth between low power and high speed, which also makes it very, very tricky on really do that at speed. And to do that, I mentioned already an AWG, arbitrary waveform generator. We are using the high performance AWGs from Keysight, programming them in a very efficient way, and then leading our signals to the DOT. So basically, we are running that on an external PC, controlling the AWG, and for calibrations, and also for the demo that you will see later, we are then capturing the signals on an oscilloscope. And when you are doing an actual receiver test, we then also have our Valley Frame test automation, where you capture your test results in HTML or Microsoft Excel format, and you then can easily compile them into a report for your customers and give it to them as a compliance or conformance test result. Yeah, generating those AWG waveforms, I said it already, it's an AWG. It's not so straightforward. What I want to point out here, that's also something that we came up with a challenging part here. When using irregular algorithms to generate signals with an AWG, you often come across the sample jitter, which then makes it really, really hard to generate clean signals, and we found a way to optimize the sample jitter to get that to an absolute minimum, to not stress your device with unwanted jitter, but to really get a signal that is as clean as possible if needed, and then only generate disturbances if you really wanted to stress your DOT. And for more of the details, you can follow up with us. It's unfortunately not enough time to do that in this demo, but of course feel free to contact us and we can give you more information about those effective waveform generations here. With this, I want to end that short live presentation. I want to thank you for your attention, and yes, I will now go for a quick demo of that setup. Hello everybody, we will now have a look at the MIPI C-PHY N5991 frame generator. With this tool we can easily connect to an AWG and send signals from the AWG to our C-PHY DOTs, either generating stress with worst case conditions or checking the nominal behavior with nominal signals. For this short demonstration I have connected this AWG not to a DOT but directly to an oscilloscope, so we can directly see how the signals are generated. First of all, this is a nominal C-PHY signal that I'm generating with as few distortions as possible, and also, as you can see here, with the optimized AWG sample jitter for this signal. Now we will modify our signal parameters and see how this affects the output of the AWG. We can go to add, for example, a disturbance, which is our duty cycle distortion. I will add, let's say, 150 milliUI, and then apply this one again to the AWG. In the meantime, while it's calculating, I can show you the other settings that we can do here in our frame generator. Just a little background information, the wait time for the calculation here, that is because we really are calculating our signals live, depending on the set parameters, allowing you maximum flexibility for changing distortions or levels, adding jitter and all those other things on the signal. That means you are not limited to just a limited amount of readily prepared sequence files. No, you can always directly adjust the signals as you need it in your specific setup. Now you can see here the download of the sequence was done. We now will have a look at the scope on our signal. And you can see here right now, if you compare it to before, we now have quite a lot of jitter here, which is called by this duty cycle distortions that I have added in our disturbance field here. We can of course also, for example, simulate ISI, adding S parameter files into our setup. So I will activate now S parameter files, and I will also actually at that point here deselect my disturbance here, because adding everything at the same time will cause too much disturbance to our signal. Again, clicking on apply, and then let's wait for our signal to be downloaded. You can see the status in our message in here. And again, while we are here waiting for a little while, a little bit more explanation here on our left-hand side. So I can of course select all kinds of different sequences following different protocol standards, either for CSI or DSI. We can of course also select various protocol sequences that are then generated here. So we are not only generating a physical eye diagram signal, we are generating real traffic here for MIPI C-PHY following the various standards that are then using the C-PHY standard here. And also, for example, here we have also the protocol timings when it comes to high speed and low power changes and so on, but this would lead too far for this quick demo here. So again, you can see the sequence was done, and now checking again the signal on the scope, we can then easily see how actually now our ISI really closes down the eye, and we can hardly see any eye opening anymore, as you can see that one here. Yes, this was our very short, quick demo on our frame generator. Thank you for your attendance, and I wish you a very, very nice day.